Yeah, Jameson said, well, Mrs. Snipes, I thought you said instead of 100 billion, there's just 200 billion stars. And I double-checked the article, and it's actually about 10 times or 20 times the amount of galaxies we thought there used to be. Now we know it's 2 trillion. So that's a lot of galaxies. And it brings consequences about like our whole universe in general. And then if you're one of those who likes to think about life on other planets, we actually think that most stars have a system of planets that orbit the stars, just like our sun has our 8 planets. So that's pretty cool. So first off, this over here, okay? The constellation Centaurus, okay? And you've probably heard of Ursa Major, Ursa Minor. That has the Big Dipper and the Little Dipper in it. You've heard of those constellations. You've heard of Orion. You've heard, hopefully we'll see some of these this semester. But you've probably never heard of Centaurus, because actually that's a constellation that is visible in the southern hemisphere, okay? Anybody know what star is named our North Star? Starts with letter P. Polaris, yes. Polaris is our North Star. And when I brought this in here today, because I think we'll kind of get to some places, this is my axis that the Earth spins on. So the North Pole, or Polaris, and I think I mentioned this the other day, we're going to make that clock Polaris. Okay, and the Earth's axis is tilted about 23.5 degrees, so that's going to be kind of what we got going on. Okay, so that's Polaris. And I mention this because in the southern hemisphere, and by the way, if you were like a navigator, okay, before smartphones and everything, okay, you could actually use the location of the North Star if you're in the northern hemisphere to kind of orient yourself. Okay, now there is no pole star in the southern hemisphere. Okay, in order to find the region where the axis of rotation points to, there's no star. So what they use, I mentioned this, is they use the Southern Cross. And I put a link on my Twitter to kind of see how you do that. But basically, you use the Southern Cross, and I can't remember, I think you go, it's like 2 the Southern Crosses, and then over here is the region, the south. Okay, so there's the Southern Pole Star, so I think that's kind of fun. This actually, though, is up here because it in the, you've probably heard of Proxima Centaurus. Was that from the movie with the blue aliens? I don't know. But Alpha Centaurus is Alpha Centauri. It's in the constellation Centaurus, and Alpha means it's the brightest star there. So it goes Alpha, Beta, Gamma, okay, to the dimmer stars within a given constellation, usually in general. So that's the closest star to us, 4.5 years away. Okay. So one of the things we'll be talking more about is where are we, and you guys told me we're in which galaxy? The Milky Way. Where are we at in the Milky Way? Well, thank goodness we're not in the middle of the Milky Way because there's a supermassive black hole there. We're about halfway from the middle to the edge, and the Milky Way is like a frisbee. Most galaxies are nice and flat like that. Yeah, and there's 2 trillion galaxies. So grains of sand, instead of being like 1 earthful, it's about 20 earthfuls. Each grain of sand that you can find on Earth, turn it into a galaxy, and then take that times 20. That's how many galaxies are in the observable universe. Now, I've kind of chased down, I'm interested in a lot of different things. I'm still learning. I think we should all learn forever. But what observable universe, what does that mean? So I went ahead and kind of read an article. It's a Wikipedia article, but it's pretty good. It talks about the observable universe and what they mean by that. So take a look at that. So the next, actually, few slides, I have a few that I took on my own. So these are things that I've taken through my telescope. The other day I got the gizmo I told you that attaches to an eyepiece, where if you have a smartphone and you're out where I have the telescope set up, you can take your smartphone, put it in that little holder. We'll hopefully kind of do some adjustments and you can get a picture. Now, this one actually, as you might imagine, if you do much with photography, you can make it like open up the shutter for a long time. And I don't know how long this was. This might have been 30 seconds, which is long for a shutter to stay open. But you see this wispy thing here? That's, I think, called the Whale Galaxy. Isn't that cool? I love it. Makes me want to get my telescope out. Can you guys see 3 galaxies here? Okay. That's actually a set of 3 galaxies in the constellation Leo. Okay, so those are galaxies. You also see the stars. So the stars would be closer to us. The stars are part of the Milky Way galaxy, and the galaxies are farther. Okay, that's kind of how that works. I think I have just a couple more. This is a spiral galaxy, and this is actually some spiral galaxies you see edge on, like kind of maybe the Whale galaxy, but some galaxies you see face on, and this is a face on spiral galaxy. I just thought that's pretty. And then the last but not least, the granddaddy of them all. This is my photograph of that Andromeda galaxy. I know, 2.5 million light years away. So, and the more, taking pictures like this is like anything else, the more you do it, the better you get at it. So it's funny, I was looking through my pictures to which ones I want to show and tell, and I'm like, oh, I did get better at it, didn't I? They'll suck. No, I did get better at it. So you can kind of see, it's just pretty. And you can kind of see it's a companion galaxy. Okay, so now back to your lecture slides. Okay. We'll be talking more about how stars live their lives. Okay, our star, and I don't think I've mentioned it yet, but our star was born about 5 billion years ago. It says 4.6. Okay, but down here, how long has our star been a star? Well, about 4.6 billion years. And it's halfway through, so it's got about another 5 billion years left. And so what's our star going to do? Okay, and we'll be talking more about that, but what stars do in the end depends upon how massive they are. Okay, so ours is kind of a middle-of-the-road star, so our star is not going to blow up. It's basically going to kind of slough its material off. I mentioned this because, and I guess I would kind of maybe start from here, the material that any star, whether it blows off or kind of sloughs off, okay, can actually be kind of material that stars can make new stars that are coming alive, can use to make themselves. So that's kind of what this is showing you. This is step 1. This is step 2. This is kind of the evolution or the birthing of a star, not the evolution. Step 2, it kind of begins spinning. You can kind of see, does it look kind of hot in the center there? Okay, that's kind of what's happening here. Kind of see jets of gas coming out from its poles as it's spinning. Most stars spin. And then here the star has turned on. Okay, so our star is right here. Ours is a full-fledged star. It's been doing it for about 4.6 billion years. But our star, okay, our star once started out like this. It started out basically as stuff that was left over from other stars. Our star is at least 2nd, 3rd, 4th generation. Okay, so that means that stars have lived their lives given the stuff to be used as our star. And when I say our star or the sun, I also mean the stuff that made up the planets too. Okay, so that's kind of, if they say we are all made of stardust, that's what they're talking about. We are not a 1st generation star system, sun and planets. Okay, we're recycled. Because only in recycling can you get some of the more complicated elements. Okay. Cool. So this is kind of neat. The way you read this, I don't know if you've ever seen something like this, and we'll talk more about the origins of our universe, but you've probably heard of something called the Big Bang, not just the show, okay? Okay, so the origins of our universe, if we started like the 1st second into the new year, January 1st, right after midnight, okay? That's when the universe, the Big Bang happened, okay? Then actually in February, and this is leading up to, we've gone a year. So the way you read this, I'll go on down here, okay? December 31st, that's where we're at. We're here now. Now, okay, and Big Bang. I'll put BB for Big Bang. That's kind of how we're looking at this. It's kind of waiting how things happened. So a month into it, our galaxy formed, okay? It wasn't until that fall, September 3rd, that our Earth formed. And when it says Earth, you can put Earth/Sun, because kind of Sun/Earth formed. In the fall, you're like, really? Okay, so that's kind of waiting how long that, what do we say, 13.6 billion years ago was when the Big Bang happened. All right, well then September 22nd was when life emerged on Earth, okay? And then if you're like into the whole dinosaur thing, that's what this kind of reminds me of, okay? It wasn't, life became more and more complex since September 22nd. And then you might recognize the Cambrian explosion, rise of the dinosaurs, extinction of dinosaurs. Okay, so extinction of dinosaurs, December 30th. And we're at December 31st, right about midnight. I just think that is so cool. And then it breaks down here on the 31st, okay, down to kind of the hours when kind of what milestones that we find very, very important. How long ago that happened relative to the universe coming into existence. I just think that is so cool. Okay. All right. We kind of wrap things up with, I think of a toddler. You're like, okay, little toddler, can you not sit still? And it's like, no, because the Earth is spinning on its axis. How could I sit still? I know. It's like, even though you're sitting still, you're not sitting still. Okay, so one of the things you already know about this class is that the Earth spins on its axis. It rotates. And one of the things, I didn't bring my Earth, but I want you to know that it spins counterclockwise as you're looking down at the North Pole. In our solar system, it's a lot about counterclockwise. And we're all into digital clocks, but you have to picture the face of a clock. And let me know if I go wrong, but I think I'm okay. So it goes like this, counterclockwise, okay, on the, looking down at the North Pole. Okay, so that's how the Earth spins.
How does it go around the sun, clockwise? Or?
Counterclockwise. It's all about counterclockwise. There are a few exceptions. He asked, if this is my Earth, okay, how does it, we know it orbits the sun, and it also orbits the sun counterclockwise. Okay, so it's doing this once a day, and it's doing this once a year, if my sun is there. Yeah, and that's not an accident. Actually, it's called the conservation of spin, the conservation of angular momentum. And honestly, that's kind of how we kind of had that counterclockwise spin when we started from the gas that ultimately made the sun. Okay, so that's one way we're moving. We rotate on our axis. We got two R's. We rotate on our axis, but the sun, the Earth orbits or revolves about the sun. So we'll go ahead and put this back in for the sun. Okay. So yeah, it's about counterclockwise. So we're going like this, okay? Like once a day, and then we're orbiting stuff. Okay. So it takes, how long does it take for the Earth to complete one orbit or revolution about the sun? 1 year. Yeah, 365 and a quarter days, exactly. Good. So we'll be talking more about this. Okay, in order to make a straight line, you just need 2 points. In order to make a plane, how many points do you need? 3. Need one more point. Yep. It's like a sheet of paper. So this kind of sheet of paper that holds the Earth as it orbits the sun is called the ecliptic. Okay, it's the plane. Now you might ask, well, what about the other planets? What do you think about the other planets? Do they go on the plane of the ecliptic, or do they kind of go woggy? On the ecliptic, yep. They don't go woggy, yep. Well, put that word up. Yep, all the planets. So what's the closest planet to the sun? Mercury. It's going to be a test question, by the way. Mercury? Mercury, what's the next question? What's the next planet? Venus? Yep. What's the next planet from Venus? Earth? Yep. What's the next planet from Earth? Mars. Perfect. Then we have the asteroid belt. We transition from rocky planets to gaseous planets. So we have Mars. What's the next planet after Mars? Jupiter. Very good. Gaseous planet. What's the next planet after Jupiter? Saturn. Perfect. And then these Jupiter and Saturn are kind of similar color, similar composition. Then we have the two blue guys. After Saturn, and I get these mixed up sometimes. What comes next? Uranus. Yep. Very good. And what comes after Uranus? Neptune. Yeah, that's it. Very good. And they all orbit the sun pretty much in the plane of the ecliptic. All right, let's see.
I have a question.
Yes.
If Earth could spin fast enough, could we fly off?
If Earth could spin fast enough, would we fly off? Yeah. And that's like a science fiction show. I think that if we could somehow make us increase our rotation, I do think that we'd have a way, we would tend to go farther from the sun. Yes?
Just like kind of curious, what would happen if the Earth were to stop spinning?
If the Earth were to stop spinning, yeah, exactly. We'd all have whiplash. Because it's funny, because, we are going very fast through space. And it's like if you're going in a fast car, what happens if the car suddenly stops? Yeah. Inertia. I heard somebody say inertia. Exactly. Yeah, your car, what you're riding in might stop, but you have a certain amount of kind of forward velocity called inertia. So we would fly up.
Would something like drastic happen if it stopped spinning? Like, would we all die?
Well, so assuming we would hold on to something so we wouldn't go flying off, okay? Or we were attached to the Earth somehow under a cave, and we didn't get crushed. The problem with that, and Mars has this problem, is if the Earth stops spinning, then we lose our protective, it's called a magnetosphere, or magnetic, it's invisible, but it actually blocks harmful radiation from the sun. And that's related to our spinning. And Mars has that problem. So that'd be a
Does
problem.
Mars not spin enough? Or?
Right, Mars doesn't spin enough, and it's kind of cooled inside, which is it's spinning and liquid mantle within the planet that gives you that. Those two things.
So do we know what causes gravity?
Do we know what causes gravity? That one I'm still reading about, because the whole what causes gravity, if you've kind of been following the Higgs boson, God particle, and everything, we understand a lot about, or scientists understand a lot about gravity, but what causes it is a little bit elusive. And I know the particle physicists, the ones that don't look, they take an atom and they break it apart into little tiny pieces, and they've been chasing it down. So those are all good questions. Counterclockwise. Okay, so we rotate, we revolve and orbit are synonyms, okay? And then also we have this other thing a few other things that are going on. So, for instance, you kind of see our little box here where the sun is the yellow one, and you see kind of the white, those are other stars, okay? And you can kind of see the green arrows. The green arrows are kind of showing you the little bobbing motion of the stars in our vicinity. Okay, so we kind of have that going on, okay? But the other thing is and there are how we saw a photograph of the Andromeda Galaxy a little bit ago? That's actually light from those stars. Well, we can't get a picture of the Milky Way galaxy. Why not? Because we're in it. Yeah. Yes, exactly. So this is a figure, not a photo of the Milky Way galaxy. And we have the supermassive black hole in here. And this kind of goes back to a little bit what we've been talking about. If the stars in our galaxy were not, they're showing it moving clockwise. If the stars were not moving like this, okay, just based upon the physics of this universe, the mass, the matter, whatever, if we're not moving, it's like if you're not moving forward, you're moving backwards, okay? If you're not moving, basically gravity is going to win out, and we're going to fall into the supermassive black hole. So there has to be motion. There has to be orbiting. So all stars need to orbit within their galaxy if they don't want to become part of the supermassive black hole in the center.
Is there a plane that our solar system lies on as it orbits?
Yes. Yes, there is a plane that our solar system lies on. The most galaxies are like frisbees, okay? And I'm not sure what we call that plane. Plane of the galaxy, I guess. But do you guys remember, was it 2006 with the whole Mayan calendar ending, okay.
Yeah.
Okay, good. And I'm pretty sure the whole Mayan calendar ending actually had to do with the sun kind of bobbing a little bit up and down relative to the plane of our galaxy. So, nothing happened, right? I just think they ran out of tablet. That's what I think.
They did have predictions actually for past that.
They did have past predictions?
But they had predictions for what would happen after 2012.
Oh, okay.
It wasn't like the end time.
And it was 2012, not 2006, yeah.
More of just their renewal period. It
Yeah.
happens once every 230 million years, I guess.
I think somebody just took it and tried to make it something apparently was not what they intended.
No,
So, what were the minds thinking if they could see us then?
it's not.
Yeah.
It's not their fault. We burned all their text.
How do we know it's a black hole and not it's a really big star?
We'll be talking more about that, but stars have a certain density. I don't know if you're familiar with something being kind of packed close or be something kind of fluffy like styrofoam, low density. A rock has high density. The thing about it is we understand the density of the object that's in the center of our galaxy, and that the only way it can have that density is if it is basically folded the fabric of space-time in on itself is what black holes do. So it's so dense.
Oh, because our physics figured that out.
Yes, our physics figured that out, and we'll be talking more about that.
What if they're wrong?
Yeah, what if they're wrong? And that's where, an introductory course like this might just kind of make you think, now I want to see what that looks like, and then you can go find out. Okay? So two other ways, our whole solar system is kind of moving a little bit amongst our stars, and more importantly, our star is orbiting the supermassive black hole. Okay. Oh. So how long does it take to complete one circuit? About 230 million years. So quite a while. Don't wait up for it. So again, this is not a photograph, it's a figure of the Milky Way galaxy. And we're going to see that galaxies, although I mentioned they're kind of oftentimes, especially spiral galaxies, are flat like this, they have kind of near their supermassive black hole kind of what we call a bulge. So it kind of bulges out a little bit. Okay. So here's one other way that we're moving. So, and we were kind of talking about this a little bit after class on Friday. You guys, do you have this one? Okay, good. A couple of blank pages. Bonus pages. So as we move, like the length of this table, I'll make this position A, and I'll make this position B. Okay, that's a certain amount of space. Okay, that's actually, we're just traversing space. We're walking in space. Okay, and actually Einstein linked space with time, which, oh my gosh, the science fiction movies that Einstein could make out. But basically, not only is this space, but it's a certain time frame that this is happening. So, at the time that the universe unfolded, actually not only matter and energy, a lot of energy was converted to a small amount of matter, but also the fabric of space and time was created. And I was trying to think of how to explain this expansion of our universe, and I think that's kind of where I came to. And so basically it expanded, and we actually think there's a time called inflation where it expanded faster than light can travel, but it's been expanding ever since, okay? So I know it sounds weird, but if I were to come back, I don't know, 100 billion years from now, and to measure this point A to point B, okay, it would be longer. Our space is expanding. Bless you. And actually that kind of brings along, sometimes we talk about the fate of the universe. With expansion usually comes cooling, and some would say that actually the matter will expand and cool to the point of just kind of a big chill out there. But I'm not sure I agree with that. Okay. So my point is, as the fabric, this here, think of, has anybody in here ever eaten raisin bread? Okay. So think of raisin bread. It starts out small, and kind of those raisins are the galaxies, okay, that are now or kind of early on in our universe. And think of the bread itself as being like the fabric of space and time, the universe expanding, and it carries those little raisins along. Okay, that's kind of what this is talking about. So the Milky Way galaxy is one of those raisins. So later on in this course, we're going to talk about how we can actually see galaxies that are moving away from us. Okay, and I know there's a little bit of galaxies. We said the Andromeda galaxy is moving towards us, and it is. But mostly galaxies are moving away from us, and this is related to this expansion of the universe. Okay, so there you go. We're
So like,
that way
so,
too.
so I guess like when the Big Bang happened, the stuff just kept going.
Right. Yep. Yep. Kept going and going. Not only that, but we're going to see that the expansion is increasing. It's increasing in movement is called speed at which something moves. An increase in speed which something moves is called acceleration. So actually it's getting larger, faster and faster and faster. And if you've done much dabbling in physics, you know in order for anything to accelerate, there needs to be a force. So anyway, it's all cool. So this kind of sums it up. Are we ever sitting still? And I'll have a test question over this. I'm not sure. Sometimes it's been my short answer question. But basically, how are we not sitting still? So you already know the first two, okay? You came here knowing that the Earth spins on its axis. And I didn't mention it, but isn't it cool that if you're near the equator, you're literally moving, flying through space faster than if you're because of the rotation of the Earth, than if you're at the poles? I just think that's neat. Okay, so we're doing that. And we're also orbiting the sun. Okay. Then the other one, okay, we're kind of bobbing amongst the stars. Okay. And we're also, this says Milky Way rotates, and that's actually the stars that are orbiting the supermassive black hole. That took us the 230 million years to complete one circuit. Okay, the next one is that the galaxy, which is the Milky Way galaxy, is moving. Okay. And actually, then the universe is expanding. So, yeah, when the little kid says, I can't sit still, you're like, I know you can't. Let me tell you why. So, good. Okay, let's take a look at part 2. Okay. Yay. Very cool. Shh. Hey, do you have questions back there? Are we doing okay? Okay. Okay. So I mentioned, like, if you want to take a picture of Andromeda, like I did, maybe you have to open your shutter for 30 seconds or something like that. And again, the pictures that I show you, I've been doing this for a couple years, so it kind of takes a while to figure things out. But if you were just to go out and open your shutter and look at stars, you would actually see those stars move and create star trails. This is a star trail photo, okay? So you're like, really? So one of the things I'm going to convince you of, if you didn't already know, is that if you're outside when it's warmer, looking at stars, you might see the Big Dipper. Right now, the Big Dipper is usually kind of low on the horizon, okay? And then you come back later, and it will actually, the Big Dipper will move, and it's there's my North Pole, right? Okay, there's my Polaris. It goes counterclockwise around Polaris. So the Big Dipper is going to stay the Big Dipper, and the whole set of stars is going to whoop up. Okay, and then if you come out a few hours later, it's going to whoop up here. And I didn't think about it much till now, but you figure it's going to complete one circuit, and I'll tell you why this is, as the Earth spins on its axis once. So it takes 24 hours for the Big Dipper to go around and come back where it was, about 24 hours. So you figure 6 hours later it'll be up here. Okay, 3 hours it should be kind of like that. Something like that. So that's kind of how that goes. So the stars appear to move because the Earth is spinning on its axis. We'll talk more about that.
Also move during the time of the year, too?
Yes, they also move during the time of the year. But here's kind of the deal. If we make this the sun, okay, and this is my axis of rotation, Yeah, I know. Okay, so you figure over here, this is nighttime, so we see those stars, okay? But there are some stars that we're gonna see over here. So we always see Polaris, okay? And then this would be, so it takes 12 months to go around once. Okay, so I'm gonna go 6 months. Here I go, here's my 6 months. I'll put my sun right here. Okay, so this is 6 months from where I was. And exactly what you said. So over here, I'm gonna, at nighttime, I'm gonna see different stars. What happens if I try to see those stars that I saw 6 months ago?
You cannot see.
I can't because the sun's in the way. Yeah, right. It's called Rayleigh scattering, and it like basically makes the skies pretty and blue. Yeah. So we do see different stars, but there are some stars that we'll see regardless. Yes. Good point.
Is that because we're in the middle?
Yes, that's because we're in the northern hemisphere. We can see a certain amount of stars around Polaris. Yeah. Very good. Okay, so what are we gonna see, what might you see if you go out to a lab and look through a telescope? Well, you might see planets, stars, galaxies, nebula, clusters of stars. But here's, and I wish I had my planet Earth, but let's see, how do we go? That's the sun, right? So this is daytime. Okay, and then it rotates counterclockwise, okay, and this is actually sunset, you guys buy that, okay, and this is actually midnight, okay, and then this would be, what, like 3 a.m. or whatever, okay, and sunrise, okay, so it does that once. So the sun, because the Earth is rotating on its axis, that's why the sun appears to rise where and set where? Is it east or west?
Rise in the east.
Yes, it rises in the east and sets in the west. Exactly. I know. It rises in the east and sets in the west. So stars are going to appear as nightfall comes. Stars are going to appear to rise in the east and set in the west. Okay, so that is north, that is east, okay, and that is west. So stars are going to appear to rise in the east. Yeah, that works. Counterclockwise. Rise in the east and set in the west. Okay. I think we'll talk about parallax later. This thing about parallax is important. Okay. But it kind of goes. Well, we'll talk about parallax later. I have some pictures coming up. This actually is called. This is part of our galaxy. I said you can't get a picture of the galaxy, the Milky Way galaxy. The best you can do since you're in the galaxy is to try to kind of see what's in the galaxy around where we are. And so when you look at something called the Milky Way, okay, that is, you're looking into the planet of our galaxy. What else do we have? Constellations. So probably as we get going, we'll be talking more about constellations, what's up. But who in here wants to know more about finding constellations in the nighttime sky? I think everybody does, yeah. So we'll kind of see what we can do. Now, there's a website down here. It's not on your, it's in purple down here at the bottom. I'm going to go to it right quick. So if you want to know about constellations, I gave you a sky map when we came today, or when we came the other day. I want to take a look at that. Copy my sky map. But you might also want something that's a little more dynamic, something a little electronic. And the thing is like I heard you guys say, these stars are going to be different than we see like in 3 months, heaven, 6 months, we're going to see different sets of stars. So, let's see if this will go to it. Oh. Let's go to Stellarium. On this slide, by the way, when I'm looking for test questions, I'm looking for the magic 88. 88 constellations. Yeah, and I brought this today. We're going to be talking about this. It probably won't be today. But you guys, what's in the middle? The Earth. Yep, there's the Earth in the middle. And then what are those yellow dots? They are stars, yep. So I'll pass this around, and I've dropped it a few times, so I don't know how many more drops it has in it, but I'll pass this around, see if you can find your favorite constellation. Now, I already mentioned that these stars down here in the southern hemisphere, we're not going to see unless we go south. Okay, so we can see these here. This, by the way, as you touch it, that is called the celestial sphere, and it's just a model. Do you think all those stars are really at the same distance from us? No. But it's a nice model because they appear to kind of be stuck together. Okay, so that's the celestial sphere. So while that's going around, let me see if I can pull up this. So stellarium.org, it's, what do they call it? It's free, it's open source. I think it's good. I think it's pretty darn safe. Oops. I need to go to here, show it. Okay, there we go. So if you go to stellarium.org, they might ask for money. I've never given them money, so but they are great. If you kind of, I guess up there is where you would click to download the right place. Okay. So I just think it's a great software. They keep updating it. So let me show you a little bit what it looks like. So this is Stellarium. Hopefully. So how many constellations did I say there are?
88.
88. Yes. And it's not letting me. Doesn't want to project it. Come on, Surface Pro. Ooh, that didn't go good. All right, there you go. Okay, so this is Stellarium. One of the things, and you're just gonna have to play around with it, but if I want to see what I can do with it, I have to just kind of take my cursor down here at the bottom. And then there's also a set of menu stuff over here along the side. Okay, so just kind of play around with it. You're going to need to, if you're doing it kind of fresh, hot off the press, you're going to have to go into that location where I said over here. This is the top one. And you're going to try to have to say it where you are. Now there is, I was noticing yesterday that there is a get a location from network. So right now it thinks I'm in Burlington, but it's close enough. Now, any sort of dynamic program like this, you can fast forward it because you're like, dude, I'm not going to see stars now. Let's say what's it going to be like at 7 p.m. So there's this window right here, and we can go ahead and fast forward it a few hours, military time. Okay, so there we go. There's 7 p.m. Okay, so if we wanted to know what that bright star is in the west, okay, we could kind of scroll around here to the west. The green things right now are meteor showers that aren't necessarily active. There we go. And this is like, you're like, oh my gosh, it's so bright. And yep, that's Venus that I mentioned the other day. If you click on it, it'll kind of give you information here. And this is Mars. I know. So how fun is that? This is 7 p.m. And then if you're like me, you kind of want to get a sense for what those stars are. Now, we can talk about constellations in here, but what really connects is when you go out to a nighttime sky and see the stars. So you're going to want to turn on the constellations. Those for this program are along here. So if I click here, it will give me the names. Oh, it'll give me the names and the stick figures. Okay. And then if I click here, which is probably what I want, but if I click here, creepy. Okay, I know. Those are real. Don't show your little kids that. Okay.
Yeah, but there's stuff up there.
Yes. That is very creepy. So that's all good. That's kind of how that works. One other thing about constellations, I told you, 88, right? Now, if you go here, see, I found it earlier. If I go to this one, I think is it configuration window? No, it might be this one. Okay. If I go over here to star lore, okay, what's clicked now is the European or something. Where is it? Kind of looking at, yeah, Western. Yeah, thank you. What's clicked now is Western. But like if I would go up here to click, let's see, I thought Korean was kind of cool. If I click Korean, see if you can kind of see in the background that my constellations change. Okay, I think that's neat. I also clicked Navajo. I thought I'd be curious what they had, and there weren't is very the whole sky wasn't filled up. Chinese, Aztec, and it makes sense because each culture has its own, you know. It could be the Aztec didn't map there's the Aztec. They didn't map everything, did they? Okay. I volunteer out at the observatory a lot, and one of the things when kids come out and we kind of look at stars and like, oh, that's Hercules. And like, no, I don't see Hercules. And then the little kid will come up with just something great, like, yes, that's what it looks like. Okay. So let's go back and we can see what else we got in our slides. All right. All right. Oh, goodness. Are you serious? Okay, we did these. Oh, okay. So, yeah, the Wednesday, Thursday kind of got in there, so just ignore that. But we'll hopefully learn more about constellations as we're in here. I'll just kind of leave it that way. But a few things, and sometimes I test you over this, so everybody's like ears kind of, anything that's on a slide is fair game to test over. You guys told me you've seen is anybody here not seen the Big Dipper? Well, I know. You're like, I don't know. I don't know if I've seen it or not, maybe. Well, hopefully we'll see it this semester. But the Big Dipper is actually what we call an asterism. Okay? Asterism. And an asterism is just like a piece. It's of a larger group called a constellation. So Big Dipper is an asterism. It's part of Big Bear Ursa Major. Now, the cool thing about the Big Dipper is you can use it to find the Little Dipper. And the cool thing about the Little Dipper is you can use it to find Polaris. So we call, see if I have a build on here. Oops, I guess not. We call these the bowl stars. Does it look like a bowl? Like a bowl of the Dipper? Okay, those are 4 bowl stars. And these are the furthest 2 stars in the bowl of the Big Dipper, okay? So once you find those, you make a straight line, and then the next star you come to actually is Polaris. Now, it's not very bright, okay? But that's how you find Polaris from the bowl of the Big Dipper. And then Polaris is in the handle of the Little Dipper, which is also an asterism. If you find the Big Dipper, and if you can see the handle and it doesn't go below the horizon, you can arc to a bright star called Arcturus. Okay. And then if you find Arcturus, you can, what we say, speed on to Spica. And then down here we have the summer triangle. Surprised I don't have this summer triangle. And the summer triangle is made up of 3 bright stars and 3 different constellations. Deneb, I'll put a 1 next to Deneb. I'll put a 2 next to Altair. And I'll put a 3 next to Vega.
Do we need to memorize these names?
No, the numbers aren't the names, no.
No, not the numbers, but like the names.
Do you have to memorize those names? Maybe, I'll tell you. On your review sheet, whatever questions I pick for the test, I'll kind of give you a hint if that's the case. And so we'll kind of finish today with a few slides of, this is our old house and we put a new roof on it. Not until you ever like take a picture, you say, oh, that roof is terrible. That's got a new roof and it's, we're gonna hopefully close on it in the next couple of weeks. But anyway, you can kind of see the stars. And then what I did was go ahead and draw what it is. So I love the constellation Orion, and maybe some of you guys do too. If you're familiar with it, it has 3 belts, and then it has kind of corner stars, okay? So these 3 belt stars are right here. And we have Taurus the bull. I like Taurus because I think it kind of has like a V. I kind of call it the flying V. And then here I have the Pleiades, which is part of Taurus. This was, actually we were in Mississippi and I took this picture. What's that a picture of? The Milky Way. Very good, yep. I kind of made out some things. So we had Mars and Saturn and the constellation Scorpius with the bright star Antares. And then this one, and if you're like me, I'm like, I look at the stars a lot, and I'm like, I don't see any constellations. But I went ahead and made sure that I kind of marked them. This actually then is the summer triangle, because we had Deneb and Cygnus, we had Altair and Aquila, and we had Vega and Lyra. So there's the summer triangle. And you can just barely make out the Milky Way. The reason the Milky Way looks so milky is because it has like tons of stars. Yeah, and some extra dust and stuff, but lots of stars. Okay, very good. Well, that brings us to that. And that's where we'll pick up on Wednesday.